When I was younger, I had interest in many of the scientists, but it wasn't until I took classes in mathematical modeling where I actually realized that you could actually use computers and use mathematics to actually build models, reason about the world in very simple but elegant ways, and actually automate it with computers. And the more powerful the computer, the more powerful questions you could ask. And so that really set me on my course to lead me where I am today. Technology and the questions we could ask and the challenges that we could take on really have been evolving together in lockstep. From the introduction of the telescope, we could look up to the skies and we could start asking these questions of how did the celestial bodies move. As instruments have come in, scientists have quickly picked up these instruments and started asking bigger questions, getting faster answers. And over the last decade, we've seen computers playing that role as well, where we can get answers faster, we can look at more data, get more accurate answers, we can pull more complex systems together like the atmosphere and the ocean models. And if you look at what's been going on in the last 10 years, these models have gotten bigger, they've gotten faster. We've used supercomputers, we've used large disk arrays to store more data for doing longitudinal studies over time. But we are really seeing a transition point right now where we're seeing the fundamental approach to science changing. And it doesn't begin with a hypothesis or a theory. It begins now with a large volume of data. Welcome to the petabyte age, where you start with the data and then start asking those questions around the data first, not starting with a theory. And so we are seeing a transition, all brought about because of computers. We are seeing a phase change, a new branch of science, one where we really can't come up with theories. So it's going to complement this current line of scientific reasoning. But there are areas where we simply don't have the theories, we don't have a deep enough understanding, and we're simply going to have just the data to begin within the petabyte range or the terabyte range. And it is well grounded in traditional science. We have from traditional science techniques like Bayesian methods that look for correlations in data. Well, those correlations over large bodies of data actually still apply, so we're still applying some of those same techniques. But again, it doesn't begin with a theory, it begins with show me what the data is telling me about the process. And from there I'll come up with a theory and drive it further. So the two generations of science are very complementary. Data clearly is taking a more prominent role in the sciences, and it's not just the availability of the data, it's about how the scientists are actually owning the data from the birth of the data to the curation of the data, where it will exist, reference data will exist for years. And Microsoft basically has a touch point along that entire pipeline. We have researchers like Feng Zhao and others at Microsoft Research who are building sensors that we can deploy inexpensively out in the field with getting high fidelity results. And the moment you deploy the sensor, you have a database schema that can immediately capture the data that comes streaming off of those sensors. Well, often you can't ask queries over big collections of data. You want to listen to basically the streaming data coming in and ask queries over that. We have technologies like Stream Insight, or a codename Orinoco was our internal project name, that would actually do standing queries over event streams so scientists could get real live monitoring over the event stream. We have data mining tools. You can come back later and look at 2 or 3 years of data. So at each point along the way, all the way even to basically curating the data, publishing a result into your Word document, you're reading the paper and you say, that's really an interesting result. You can click on the data set and it will take you back to the reference data set up in the cloud. It's not in the cloud yet. Right now it's sitting on a SharePoint server. But what it shows you is that basically we can now have a lineage and actually a connection from the birth of that data to the published result and allow readers to go back to the data. And you say, what role will the cloud play in cloud scale? Well, we're looking at how could we actually curate large collections of data, multidisciplinary, multinational data sets in the cloud as a repository for the whole world research community to use, and even have a platform for research on the cloud so that when you want to do analysis or even data visualization, that process is being spun up on the cloud. And so a researcher with a good idea in India can start up a computer with a web browser, make a connection to the cloud, and actually start asking these questions using our cycles in the cloud to do the analysis over our curated data sets up in the cloud. The cloud is really going to be a game changer. It's a game changer in many ways. It's a game changer for science, and it's also a game changer for computer science. And so the chance to actually have input on what the cloud should look like, what kind of facilities do we want to have in the cloud for doing research, motivated me to actually move to this new position. Our charter is to basically position the cloud as a platform for doing research. And we're looking at two ends of the spectrum. One end of the spectrum are the big data sciences, the large science projects, the Hadron Collider. I mean, there's a series of projects at one end of the scale. But at the other end of the scale is just the long tail of science, the researchers who 4 or 5 people want to get together, ask a question, no resources, they'll completely provision it. And so my job is to find out by talking to these various scientists, what are the services they want to have in the cloud? What are the reference data sets they would like to have to begin their studies in the cloud? And how can we have them waiting for them when they come up there on Azure? In the next 3 to 5 years, we're going to be defining what cloud computing looks like. In the longer term, we're going to be looking at cores up to 50 to 100 to 200 cores per chip. So the multi-core architecture, our key aspect, that all the way up to quantum computing. And other issues of scale are power. So our team is actually looking at how can we run our data centers in very environmentally friendly, very power-friendly ways on low power, efficiency, different architectures, maybe even different architectures for the data center. So across that entire spectrum of architectures and programming models, we're actually doing research at each single point along that spectrum. And as these systems scale, it becomes more and more difficult to program to them. So we can talk separately about Dryad and Dryad Link, but really, how do we simplify this programming abstraction so that users don't have to think about programming hundreds or thousands of cores? They simply express their intention to get something done, and the programming model will map that out to the various resources, be it a multi-core architecture, multi-node architecture, or even a multi-data center architecture. So how do we simplify that and actually make the programmer more powerful? And you see we're up-leveling the abstractions. When I was younger, I had to worry about memory allocation, pointers. Now in .NET Managed Code, we don't have to worry about memory. The system takes care of memory. Well, fast forward 5 years, we won't have to think about allocating a hardware. The system will just take care of that for us. It will take care of making our footprint in the data center smaller and larger based on our demands. So that's the future we're trending towards in the research projects we have going on. Pick any domain, be it economics, be it earth modeling, biology. It's a very labor-intensive process still. You start by rounding up data sets, you start by rounding up the hardware on which to run this. You can measure the time from idea to execution, 6 to 9 months. And that's assuming you're not waiting for funding. That's the lag time any good idea has to pay. And many good ideas go by the wayside because you simply don't want to pay that price. Imagine a day when you're going to be able to go to the cloud. The data sets that you need are either there, or there's a tool to get your data set from your computer into the cloud with the click of a button. And we will be there. Once it's there, there's a mart of models that you can select from. Deep analysis tools. We've talked a lot about big data. Coming along behind that are going to be very deep, statistically rich tools for analyzing it. Imagine being able to say, this is my intention. The models that you're looking for come in scope. You look at the models, you see they're semantically annotated, they're actually socially annotated. Who used it? What study did they use it? What paper did it impact? That looks like my analysis. That's what I'm interested in. Let me click on that. Let me click my data set. Oh, that's interesting. Let me do some visualization. These tools will be up there. So the connection between what's been going on in search and what we're trying to do in data-intensive computing, I'm actually going to give credit to Randall Bryant at Carnegie Mellon University, who actually challenged the community. And Randy said to the community, if a teenage boy can ask a question or query about his favorite music star and bring thousands of computers spinning together to actually bring back an answer in a fraction of a second about this particular star, why can't a cancer researcher ask those same questions over terabytes of data? Now, many of us who are actually building tools for scientists stood back and said, that's a very good question, and we do in fact have the technology. So what inspires this work? Because it's gone beyond just simply getting a paycheck or building software. It's really about how we can change the world we live in. And everybody in our group is very focused on, could the tools that we're building have a real impactful difference? Not just a demo, not just for the company bottom line. Will this make a difference that we're all going to benefit for? Are we going after the right grand challenges? And what can we focus our efforts on for the next 3 to 5 years that will truly make a difference? We'll look back and say, we had a part in that.